Good morning. Today's topic is effect of heteroatom in heterocyclic chemistry. That can be categorized one in this lecture, and this is one of the most important topics in heterocyclic chemistry. Reason being, if you can understand very carefully the effect of heteroatoms on the reactivity and physical properties, then you can master the heterocyclic chemistry very nicely without going through the each and every details of the particular reactions or particular class or particular topics. There are few points which have to be noted. The first thing, that what kind of effect we are expecting. Normally in the area of effect of a heteroatom, in this case I will be talking about, let us say, nitrogen maybe. This would be our main focus, nitrogen, and what you have to do, you have to compare the reactivity or all other effects with the carbocycles. That is important. That means your reference or the background material would be the carbocycles. So, our reference would be carbocycle. Then when you say so, then that means you have to first define what are the carbocycles you like to refer to. One of them is cyclohexpropane, because it is most strain and all of us know, and then we will compare with cyclohexane, that is strain free, and then also one more which belong to the aromatic compounds, that is basically the benzene ring. Now, when we consider the effect of heteroatom, when I say so, that means basically nitrogen, sulfur and oxygen. Now, often I will just give the examples with nitrogen, which can be extended to other heteroatom. So, when you let us say talk about the cyclopropane chemistry or the corresponding aziridine chemistry, then you have to basically compare cyclopropane and aziridine. Okay. Similarly, in case of cyclohexanes, all of you can guess, just replace one CH2 by NH, and that would give you this one piperidine. And likewise, in case of aromatics, so you have to compare with pyridine. So, that means the transition is basically transition of knowledge or background of the knowledge would be based on benzene chemistry, and you can also compare benzene with pyrrole. So, likewise furan, thiophene, etc. So, that means the heteroatom is there, but the ring size is changed, but both. So, they are basically the representative members of, as I told you in the last class, it is a member pi excessive and pi deficient heterocyclic compounds. So, that means throughout the class basically we will compare the chemistry of aziridine or the 3 membered cycles or the strain system with cyclopropane, or the or cyclohexane should be compared to piperidine, and likewise all other heterocyclic compounds should be, that means all other aromatic compounds should be compared with benzene. Now, so given all the facts let us say put together, you can divide the effects into 2 different categories. What are the 2 different categories? The first one is physical property. This is very important though. Many of us we ignore, we want to know only the reactions, but that is not enough. Physical property is very important, because you can extrapolate that too into chemical properties, and then of course, then you can do all reactions in invent reactions and then the chemical properties, and both the kinds would be useful. When I say physical properties, then of course, I think you have to know what it is, like say bonding. Bonding is a physical property, but since we are organic chemists, we will I think start with resonance. Resonance and solubility is very important, especially in case of the heterocyclic chemistry, because to isolate the compound, purify the compounds, you have to have pure understanding of this solubility. Then boiling point, of course, that is good. And then what? Spectral property, spectral properties, properties, that is also important. And what more? What more? And could be anomeric effect. Anomeric effect also is a kind of effect of the bonding, etc., but that is manifested elsewhere, but these are the things you have to think about. Whenever you come across a situation, first think about the physical properties, bonding properties, then you extrapolate to the chemical properties. Okay. And so, all these properties would be manifested in the chemical properties. When I say chemical properties means, I think very first thing that we talk about is loud reaction, no, acid base properties. This is basically chemical properties though. So, acid base properties. So, that means whether acid base properties, that means whether the acid strength has increased or decreased, etc. Then of course, all of us know the next important thing in the area of especially heterocyclic chemistry is substitutions, substitution, right. And then I think many of us know, I think in when you are talking about this is called neighboring group effect. This is also, that means there are few things you have to remember though. What are the area you want to explore, or you want to remember, or you want to know. And then there are a few things, special things. For example, this is important in heterocyclic chemistry, ring opening. So, ring opening is not very common in carbocyclic chemistry, but when you come to heterocyclic chemistry, there are ring opening, reopening, and then re-closing, all these things are often encountered. And then there is a special category, I think there are two kinds of special category that would be taken up in details in another full lecture, that is called tart amino effect, or sometimes tertiary butyl amino effect. So, this is one of the very important fascinating area where you can do all kinds of new molecules. And lastly there is another important area, that is called alpha metallation. I will give you one or two examples of alpha metallations. So, that is also important, that we will talk about as we go proceed. These are all, that means these last two are very important. It is very uncommon though, and they are particularly attributed to the presence of an heteroatom. If you do not have the heteroatom, you do not like to see such things. Okay. So, let us take up the cases one by one. For example, when you talk about the physical physical properties, that means the resonance. So, what do you know about the resonance? I think all of us know resonance. What to know about resonance? I mean, I can give you for example, benzene, all of us know resonance energy. How much? No, okay, new unit, joule. Joule is the SI unit, right? So, I think we should remember the SI unit, 150 kilojoule, 150 kilojoule per mole. So, likewise, then pyridine, how much? 117, and thiophene, 122, and then pyrrole 90, and furan 68. So, this will tell you something. So, that means basically what you have to find out, you have to find out the trend, you do not have to remember the value. What is the trend? The trend is, if you do not change the cycle, the ring size, with increasing the electronegativity, this is important. Electronegativity all of us know, right. Among all these heteroatoms, oxygen has the highest, next highest is nitrogen, then sulfur marginally electronegative than carbon. So, we know all these things. That means as you from the data you can make out, without changing the ring size you will see the resonance energy decreases with the increase in the electronegativity. That is it. Let us say from benzene to pyridine there is no change in size, but then resonance energy decreases. Okay. And among these, for example, thiophene, furan and pyrrole, again the thiophene has the highest resonance energy, followed by pyrrole, followed by furan. This is true. This is for example, let us say now if you take fused systems, for example, naphthalene will have higher resonance energy from benzothiophene. So, benzothiophene and benzopyrrole is basically nothing but indole. So, then benzofuran. So, this is the order. That means again it complies with this trend, previous trend, that is electronegativity increases, resonance energy decreases. But that is not always the case. In certain cases you will see that there is a difference. For example, if you take the isomers of the previous examples. So, among these, at least what has been found, this is isoindole, this is isobenzothiophene and this is isobenzofuran. So, that means if this fusion is changed, they are named as iso series. And what you see here, this is nitrogen, this is sulfur and this is oxygen. So, there is a bit of change here in the resonance energy. That means, but most cases what is seen, the resonance energy is perfectly alright, but in iso series sometimes you may have a difference in the resonance energy. Okay. Next thing, what? Solubility. Solubility all of us know. How do you basically how do you correlate solubility with the presence of the heteroatom? This is also very important. Solubility is a very serious concern in medicinal chemistry, because all the drugs have to be soluble in water. So, one of the major concern in development of a drug is to make it water soluble. For example, there are many organic compounds, many heteroatom containing organic compounds or medicines are known in the literature. They have been converted into salt. Let us say some sort of salt, means carboxylate, trifluate, bisulfate complex, then hydrochloride complex. So, hydrochloride salts. So, they can be solubilized in water. So, that means, and all of us know between nitrogen, sulfur and oxygen, of course, nitrogen is most basic and it can undergo protonation. So, once it forms this protonated nitrogen, that can undergo hydrogen bonding with water, hence solubility increases. That means, aniline is not water soluble, but all of us know that if you add little bit of acid in it, HCl, then it undergoes solubilizations. So, this is pretty common, but then you have to know this is only true for the nitrogen compounds, not for oxygen and sulfur compounds. That is that you have to remember. Okay. And dipole moment is also important. Dipole moment is also important because it can give you some idea about the boiling points, There are quite a few examples that if the dipole moment increases, boiling point increases. There is one more important point about the boiling point. How do you corroborate boiling point with other physical properties like dipole moments and molecular weights? Okay. See, these are basically the two parameters of phenol. There are other points too. I mean, boiling point. What are the factors dependent on boiling points? First is, I think the commonly known parameter is molecular weight. If the molecular weight goes up, then boiling point goes up. The second important point is packing, geometry structure of the molecules. If the cis alkenes and trans alkenes, between the cis and trans alkenes, which one has higher boiling point? Anybody knows? See, the trans means nice stable arrangements, so they can pack among themselves, and so that means that the trans will have higher boiling point than the cis. The cis will be lower boiling point. So, likewise, and if you know the dipole moment also induces rather can be attributed to the boiling point changes. If you have higher dipole moment, boiling point would be higher. So, these are the 3 important factors, but there are no linear correlationships, but with little experience you can make out where dipole moment is important, where dipole moment is not important. But in case of heterocyclic chemistry, dipole moment is important, because you are putting a heteroatom. So, you are putting in carbon and heteroatom bond polarized. So, automatically you will have a dipole moment change, and dipole moment change would induce this boiling point change. Let me give you just I think I have quite a few examples, but I will give you just one example that would tell you. Let us say furan, for example. Furan has a boiling point is 31 degree. This is 31 degree is a boiling point. Okay. And what is the dipole moment? Dipole moment is 0.71 dy, that is the dipole moment. Now, just think about this one, think about this one, tetrahydrofuran. What is the boiling point? THF, all research scholars, THF will have boiling point. Okay, I will make it like this, have that 70 degrees. So, why this boiling point? We have only increased 2 units of 4 units of atomic weight, right, or so molecular weight has been increased by 4 units, and but the boiling point has enormously increased, double, more than double. Why? And this can be attributed to a high dipole moment, right. Now, what is this? Ether. So, how much you have increased? So, that means from tetrahydrofuran to ether, what is the molecular weight increase? Only 2. So, that means boiling point should be around 70, but how much you get? Okay, let us make it 35. So, why the boiling point decreased? This is a clear case of dipole moment. In fact, sorry, I do not have the dipole moment in this. I used to have, there is a gas phase dipole moment. I do not remember exactly, but I can tell you it is definitely less than 1.75. So, 1 point, let us say make it 1.3 maybe, and this is just a guess, and this is gas phase. You just look up the Google, you will see the dipole moment is lesser than this one. So, that okay. So, likewise you can have other examples. Then other important things about these physical properties. For physical properties, we are still talking about the physical properties, the chemical shifts in NMR. This is that means NMR structure determination is very important in heterocyclic chemistry. So, what you will find very interesting trend in the for example, what is the chemical shift of this carbon? When I say so, that means basically the delta values, right, delta values, chemical shifts. We are comparing with the carbocycle compounds, and what should be the chemical shift value? Let us say if you this one take furan for example, let us say oxyten for example, and in case of cyclopropane the chemical shift value is 0.22, is less than aliphatic compound, linear aliphatic compound, because of some reason. What is the reason? Suppose alkane is 1, cyclopropane will have a very reduced chemical shift value 0.22, because of the shielding anisotropic effect, shielding, just reverse of the benzene ring, Okay. So, as if these banana bonds as if would create a shielding atmosphere, so that the hydrogen goes to upfield, that means the chemical shift value is reduced. Okay. But when you go to the epoxide, basically you are increasing the electronegativity, right. So, electronegativity. So, chemical shift value in this case epoxide could be to 2.54, that is quite obvious. Electronegativity, that means by placement of heteroatom you are increasing the electron density, electronegativity of the atom. So, and it pulls the electrons and density towards oxygen. So, chemical shift increases. So, likewise, so if you have let us say aziridine, so one would expect a the CH2 to appear between cyclopropane and this, because it is less negative electronegative than this, and it is 1.51. Okay. So, but so what about this one NH? What should be the chemical shift value? 9. See, that is the thing, that is what good, at least you have said so, but it is not, it is 1, it is 1. Again the shielding, because of this ring current it actually shields all the 3 membered rings etc. For example, I will just there is a very clear cut way, for example ethylene glycol. Ethylene glycol, what should be the chemical shift value of the circled carbon? See, normally if you have a heteroatom, the corresponding carbon hydrogen would have normally 3.5 or so, 3.5, but you have a neighboring oxygen here. So, and this comes around 3.87. Now you see the difference. What is the difference? 3.87 goes to 3.54, sorry 2.54, that means drastically decreased. Why? When I say drastically means less than more than 1 ppm. So, why has it decreased? See, this is also a nice test for whether you have, let us say you are handling with alicyclic compound, you are trying to make it a cyclic compound, cyclic heterocyclic. This is especially in 3 membered ring, you can very clearly see whether you have got the cyclized product or not. Okay, this based on this change in the delta values. Okay. Once again, this is, I mean because of this anisotropic effect of the cyclopropane ring systems. Okay. And so, I will give you one more example just to emphasize that these chemical shifts are distinctly different for a heterocyclic compounds. Like say if you are thinking about, let us say a molecule of this kind, this is a known compound, and in this case methyl group is here, and you are you want to let us say want to carry out a reaction of this kind. How do you know whether reaction has taken place or not? How do you? Okay, in aromatic portion normally there are quite a few peaks are there. So, it is very difficult to do the integration. Okay. Let us say I think I will straight away come to the problem. Circled carbon hydrogen, the starting material, it appears at 4.8. Now, you have to predict this effect of heteroatom or other things. Here this circled CH2 chemical shift after the cyclization. You do not have to give me the value, just tell me what is the is more or less than 4.8. So, you understand chemistry, basically you do not have to go through the book, you can predict with confidence whether it should be more than 4.8 or less than 4.8. Okay. You know NMR, you know amino chemical shifts, the only thing you have to basically predict and with confidence. Value would be increased, the value would increase because see now this ring is aromatized. So, when I say this heterocyclic ring is aromatized. So, when you have aromatic anisotropic effect would induce this. So, the value is increased and exact value is actually 5.18. Okay. Now, the fourth that is I think this is also you all know is strain energy. Strain energy of a cyclic structure. So, normally cyclopropane is our again a reference. What is the strain energy for cyclopropane? So, some of you probably know it is 27.5 kilocalorie, and then what should be the strain energy for the aziridine? Aziridine it is slightly less, I think I will just give you the data, it is just more or less comparable, and this is 26.7 kilocalorie per mole. So, likewise epoxide or oxygen also will have a very similar strain energy. What does it mean? So, these are all the physical properties, the strain energy etc., the calculation bonding from it comes, and then of course, it is validated by the experimental results. But now what do you see, what is the manifestation, what is the manifestation? They undergo ring opening reactions, all of them undergo ring opening reactions. Now, depending on the, now you have to know a little bit of more chemistry, but one common chemistry is that all of these strain ring system would open up if the situation demands, or situation is such that the reaction would favor this thermodynamically favorable, it will undergo ring opening to give you the ring open product. Okay. And we will see more example, but maybe just very little quickly we can see some of these acid base properties. For example, many of you have to know acid base properties, or let us say between aziridine, let us say. So, acid base property means it is basically the chemical properties. Now, onward we will talk about only the chemical properties, acid base property. Okay. In case of aziridine, for example, what is the basicity? It is more than, when I say so, that means in this case we will be talking about, let us say, dimethylamine, for example, dimethylamine. Compared to dimethylamine, what is the whether it is more basic or less basic? Cyclic. So, it should be more basic or less basic. That means what you have to do, all of us know, right. So, normally we talk about the corresponding this. Now, we have to see which one becomes more stable. See, in this case it is an open chain compound, it can readjust the structure according to its opinion, that means it becomes more stable, it is less stable. That means which one is more basic? More basic? No, dimethylamine. Dimethylamine is more basic because it gets the stabilizations on protonation, but this is not. So, aziridine is less basic, but aziridine is more basic than aryl amines, that you have to remember. That means the basicity of aziridine is in between the aliphatic amines and aromatic amines. Okay. So, this is, I think, that means basically what we try to say, that presence of heteroatom would induce these, or rather would change this acidity basicity. Okay. Let us look at with this let us look at some of these examples of these manifestation of strain. See, manifestation of strain, for example, okay. Let us say, or maybe I can just give you another example on this anomeric effect. Anomeric, we have all studied anomeric effect in heterosector, rather in carbohydrate chemistry. What is it? Anomeric effect is basically the effect between the anomeric oxygen and the corresponding the substituents. So, due to the anomeric effect, the axial isomer becomes predominant isomer compared to the electric. So, that is also true for the nitrogen heterocycles. I will just give you an example here. Someone wanted to make a free sorry, this is not nitrogen, this is carbon, free aminoaldehyde, and this is CBZ, this is a protecting group CBZ. Now, if you do the hydrogenation palladium charcoal, so what you are supposed to get? You are supposed to get this is NH2 and this is CH2PH, right. CBZ means carboxy benzoyl. So, but these sort of compounds are not stable, this simply because you have an aliphatic amine and aromatic amine. Say undergoes shift phase formations, automatically undergoes polymerization, they are not very stable. And so, to stabilize, actually the reaction was carried out in case of in the presence of trifluoroacetic acid, and if you do so, what you will get? You will get actually that I think you should have rather obtained the corresponding trifluoroacetate salt, but that is also probably not stable. So, what they did, so after this reduction they treated this with methanol and methanol. So, result is this was NH2 and this trifluoroacetate salt, then this is the benzyl, and then what you get is the hemiacetal. So, this is not a heterocyclic compound, but just I am trying to tell you this effect of the heteroatom, it polymerizes aldehyde. But then when you treat this with potassium cyanide and methanol, one would expect that this expected product is what, this NH2 and this should be cyanohydrin, just aldehyde reacting with cyanohydrin, but it is not a product here. The product goes to piperazine, and which is like this cis, and I think this is trans. So, I think we will see that whether yes, this is trans and this is cyanide. So, the presence of heteroatom, what does it do then? Presence of these heteroatoms actually makes this aldehyde also more reactive. So, eventually it goes to the dimerations. But if you take the structure, this excess structure of this molecule, what you will find? You will find a nice orientation, and which would be like this, hydrogen, and this benzyl group is axial now. This benzyl group is equatorial, and because they are cis to each other. And what else? What you will find? This cyanide is now axial, and this cyanide is axial. So, what does it mean? Anomeric effect. So, it is a clear case of anomeric effect. Anomeric effect means if you have a heteroatom in the cycle, that would alter the conformation, conformation of a substituent alpha to that, and due to these dipole interactions, dipole repulsion. Okay. Or some people talk about these overlap with the antibonding orbitals. Okay. And so, that means the presence of this is basically again an manifestation or extrapolation of the physical properties. And I will just give you one more example probably, as I will skip some of the things. For example, if you let us say try to prepare an aminoaldehyde, let us say. In this case, you see here now we are talking about the heterocycle, right. We are talking about the heterocycle. If you react this with Dipole, and all of us know what is expected, Dipole is so selective towards ester reductions to the aldehyde. So, you will guess this. Now, what it is? It is an aminoaldehyde, right. In the previous case it was not very stable. So, it got further, it underwent further reactions, and but in this case let us say if you want to stop this, is it possible or not? Is it possible or not? Well, if you compare, let us say if you compare an open chain compound, that is what you have to do. It is a cyclic compound. Now, you have to compare with an open chain compound. Open chain compound, if you have an amine, and then let us say if you react with aldehyde. So, what you would expect, you said amino aldehyde, right. This is in presence of acid, it forms this ammonium ion here, and then it undergoes, so, or iminium ion. So, it undergoes all sorts of reactions, and then you can do sodium borohydride, cyanoborohydride, it can convert this into directly amine, etc. But now it is a case here where if you have aziridine for example, a similar case let us say take SN heterocycles now. So, in this case what you have to do, you have to let us say think about in reactive intermediate of this kind. Now, whether this is possible or not. So, that okay. So, see this is now tetrahedral, this is now tetrahedral. I mean, so I mean nitrogen is considered to be tetrahedral here, and so that means it is approximately, I mean let us say 109 could be etc. But when you just like sp2 carbon atoms, if you flatten it, this angle increases. So, that means you are further increasing the strain, that means this is less favorable, this is less favorable than the previous example. So, what it means that you can actually isolate this compound, but really in reality what you will find actually it was not isolable, but it was sort of in it underwent dimerations to the cyclic structure here. So, it underwent cyclization to this one. So, it is essentially it is a dimer of this one, and what happens, this one more aziridine nucleus nitrogen attacks the aldehyde, it forms this OH here, then OH undergoes further intramolecular addition to this aldehyde to give you this lactol kind of things. So, how do you know this? This was isolable, and if you simply just react with sodium borohydride, you can get the stable molecule of the stable amino, this aziridine alcohol, aziridine alcohol. So, yes,
this one intermolecular cyclization is there.
this one,
This one.
yeah, yes.
So, is there any possibility of intramolecular?
Actually, first is intermolecular, the second is intra. Okay. So, let us say if you just look at this here, this is aldehyde, right, and this is R, and then you have nitrogen here pH, and this is CH aldehyde. So, what it does, this goes to this one and this goes to this. The first is intermolecular, then second is intramolecular. Okay. So, basically it is dimerization, that means that this is although supposed to be stable, but it is not stable, but they can be I mean in equilibrium unlike the other example. Okay. So, that means what it says, the ring strain has induced a little stability to this aziridine aldehyde. So, that means that can be, that means made use of some other ring transformations. Then other important area, that is of course in heterocyclic, especially in non-aromatic heterocyclic, is ring opening. So, all of us know, right. If you have for example aziridine here, and if you treat this with 2 molecular let us say 2 times of HCl, 2 times of HCl, what do you expect? So, HCl means acid base reaction. So, first it will undergo protonation, then what? That means the first step one would say that this is a quaternization and this, and next step. So, this is how we have to predict. That means our foundation is based on carbocyclic chemistry. We know very good chemistry of the carbocyclic compounds. Okay. So, what next? Ring opening, of course. So, we have now, that means strain energy now is physical property, now is changed to chemical property, ring opening. Now, this is the chlorine. So, the question is why does it react? This chlorine actually so this is a continued research, this is a topic of the continued, even today people are working on this as a ring opening. Okay. So, now this is now activated, a proton has made this even more activated. Okay. Because there is a charge separation possible, and so in this case this there are all possible, the chlorine can attack here and here, it depends on the balance of the negative electron balance of the substituent effect, but in this case it attacks this in the fashion of SN2, and what we get is now this one NH2, of course, then once NH is formed, then it picks up one more molecule of HCl. So, it eventually gives you basically this amino chloride. So, likewise, for example, if you take even aromatic amine, for example, aromatic amine here and take thyrine corresponding sulfur compounds. So, what you are likely to just basically heat, nothing else, you do not have to do anything, heat, and this 3-membered ring opens up and to get the corresponding mercaptan. This is not restricted to 3-membered ring. If you have, let us say, what is this name, agitidine, 4-membered ring, agitidine. Now, take methylamine and just heat it. That means amine and amine. So, they should not react, they should be compatible with each other, but the reaction it opens up and it gives you the corresponding NH2 here and NMe. So, then you get the diamine. So, that means it is a pretty common phenomenon, and so likewise you can also just think about this oxytane. Oxytanes also would give you the corresponding methylamine, sorry, this is hydrogen. So, you will have this corresponding amino alcohol. So, like this you can get all kinds of the ring opening, and one of the famous ring opening reactions, I think many of you probably would be knowing, this is taught in alkaloid chapters, von Braun ring opening, or von Braun reaction. What is it? It is a reaction with cyanogen bromide. It is a reaction with cyanogen bromide. For example, if you take N-butyl agitidine, and then the reagent you have to, this is a particular reagent, only reagent that is actually used in this reaction. It is known as cyanogen bromide. So, what do you expect? You have a tertiary nitrogen here, and what is expected out here, once again the name tells you cyanogen bromide, which one is positive, which one is negative? Br is no, cyanogen bromide. So, bromide is negative. So, that means the intermediate would be, so ide is negative. So, that means cyanogen is, cyano group here is plus, and this is pretty readily available, and this is pretty old reaction also, but very in many cases it is pretty useful. In peptide chemistry also, in peptide chemistry if you have cyclic structure, you can I think I have forgotten, it could also probably is used for disulfide cleavage, I do not know. You do you know anything about that? Okay, maybe this could be your homework, cyanogen bromide in peptide chemistry. Okay. And but in this case, so once you have a quaternary nitrogen, then what is next? This bromide can attack this alpha position, this alpha position, this alpha position, these two are equivalent. So, that means you have to decide which one would be attacked. Okay. And obviously, now we know the heterocyclic chemistry, we know the ring strength. So, this one would attack, so that the ring would open. So, that means the product would be 1, 2, 3 nitrogen, then butyl, and then you have cyanide, and here you will have the bromide. 1, 2, 3, 1, 2, 3, sorry, one more, actually it is less. So, it should be bromide here, 1, 2, 3 nitrogen, this butyl and this cyanide. So, this is a pretty common kind of reactions, pretty useful reactions. Then what else? And there are other let us say other important reactions. That means this ring opening is pretty useful. There are plenty of examples, you can take it up. Then I will just tell you one more important thing. In case of heterocyclic chemistry, the effect of nitrogen to stabilize radical carbocations and carbon ions. This is important. Nitrogen can stabilize the alpha carbon ion, alpha carbocation, alpha radical. This is very important, and you will see throughout the carbon nitrogen chemistry, and that means nitrogen lone pair can stabilize nitrogen stabilize cation, anion and radical. So, this is important, and for example, I mean it can also induce, let us say, pinnacle rearrangement, for example, and that in that case it would be known as pinnacle rearrangement, pinnacle rearrangement. So, if you treat this with, let us say, BF3 etherate, BF3 etherate. So, what would you expect? Yes, what? Fine, then what? See, okay, that is perfectly all right. So, you coordinate. So, like in the previous example is undergoes coordinations. So, nitrogen is quaternized, right? Nitrogen is quaternized, fine. Then what next? It will ring open, fine. That is also perfectly all right. So, it will have a ring opening. So, ring opening BF3 and minus and this. Now, what it is? You have to, this important structure, the intermediate has to be identified. What it is? If you recall, it is very similar to pinnacle rearrangements. If you have pinnacle rearrangements. So, in the pinnacle you had an OH group here, in this case you have nitrogen, that is the reason as a pinnacle. So, what you would expect, this methyl group would migrate and this would quaternize, okay, and this would quaternize. So, in this case, sorry, you have a tosyl here and tosyl. So, the result would be that the product, that means you will have N tosyl. So, you will have this corresponding imine. That means, this is a case of as a pinnacle rearrangement. So, that or one can say that basically nitrogen stabilizes the alpha positive charge. Let me tell you one more important fascinating reactions, again driven by nitrogen. What I say here, tertiary amino effect. We will give more example in one of the later classes, but tertiary amino effects, or sometimes we call tertiary butyl amino effect, tertiary butyl amino effect. What is it? It is a reactions of this kind. It has to be some sort of aromatic compounds. Then you should have activating groups and E2 and E2, right, and then a tertiary amino group. So, in this particular example we have one more tertiary amino group, just to show you that only one of them would react. Which one would be react? And the reaction is so simple. Just take this molecule, neutral solvent, butanol and heat. So, what do you expect? Normally one would expect you have butanol and ester. So, you are expecting a trans-esterification kind of reactions, but you do not see this. Trans-esterification normally requires either acid or base, but in this case what you have to recognize the presence of the heteroatom, and at the same time also you have to notice that this is a tertiary nitrogen. So, this is also tertiary nitrogen. The reaction actually goes to give you a new heterocycle, and this is nothing but it is a sort of a rearranged heterocycle. This, that means and this is E2 means the ethyl ester, E2 means ethyl, you get this compound. Okay. So, what do you see? What is the change do you see? You see basically the alpha nitrogen, what I said before is alpha nitrogen. That means in this case it stabilizes the alpha carbonium ion. Actually this hydrogen is shifted mechanistically. mechanistically this hydrogen is shifted, okay, or you can say, so first I mean so many things happen, let us say it goes to via this thing that thing. So, eventually as if what we can say, I think one of these intermediate could be written this way, you can just sit down and work it out as if this hydrogen is shifted here and then this nitrogen is formed, okay, this is shifted here formally and this, and what else. So, it is a neutral compound. So, it has to be neutral, that means this is the negative charge, the negative charge. Then this negative charge then intramolecularly attack this. So, eventually give, and there are plenty of examples, people are actually using this sort of molecules this one. So, we will have more examples in one of the later classes. I think I do not want to talk about these neighboring group participations, all of you know nitrogen mustard, right. What is the nitrogen mustard? What are the structural features? You have to have a heteroatom CH2 and a leaving group, right. So, these are all, that means basically the effect of the heteroatoms on the reactivity. And the last example I think I will tell you, this is alpha metallation. There are plenty of examples and it is applicable to both saturated and unsaturated molecules, both saturated aromatic and non-aromatic molecules. Okay, I will just give you one example, quite fascinating. Let us say if you begin with indole, and I think first butyl lithium is given, then carbon dioxide, then again tertiary butyl lithium. First one would remove NH to convert this into carboxylic salt. What next? It will actually lithiate the alpha positions. This is the trick. That means basically that heteroatom induces the alpha lithiations, and if you treat this with let us say diiodoethylene. So, what you would expect that we will be getting is 2-iodo, because this is a carbon ion. So, this is a nice source of, similarly dibromoethylene also is a source of bromine in the metallation reactions or this reaction with metallic species. So, you get the iodo, and this corresponding the carbamic acid, all of us know after the acidification is unstable, it loses the carbon dioxide. And I do not have the exact example now, but there are quite a few examples. Let us say if you have for example, you have to have some electron withdrawing group here. If you can use secondary sec-butyl lithium, you can expect this lithiation at the alpha position here, you can get lithiation at the alpha position. Okay. Even for this is also true for the pyroledene, piperidine systems, but you have to have a carbonyl group here and there, so that it can stabilize these corresponding lithiated species. But that is also driven by the stability of this nitrogen. That means, in this case there are two possible CH2 groups. Of course, all of us know that this is a benzylic one, so it will be lithiated. Okay. And what else? So, summary physical properties. So, you have to list the physical properties, you have resonance, solubility, boiling point, spectral properties like chemical shift, etc. Okay. And chemical properties mean acid base. Next one is substitution. We have not talked about substitutions. See, in case of benzene, all of us know substitution is guided by the presence of the groups. So, in heterocyclic chemistry, in case of pyridine, the substitution, electrophilic substitution for example, takes place preferentially at 3 position. So, that is what you have to remember. So, that means in case of benzene, let us say it depends on the substituent here, but in case of pyridine you can think about, well, this is the substituent maybe. So, in that case this is ortho and meta, that means basically this is the most preferable position, preferred position of the electrophilic substitution reactions. And if you have a 5 member ring, the 5 position is the most preferred one. So, the one that means this one, or you can say 2 or 5, and in case of pyrrole it is 3 position, 3 position is. So, these are the things you have to remember. And you can also, if you don't, if you have forgotten, what you have to do, you have to write the, what you have to write, you have to, let us say if you have nitrogen here, here you have to write the corresponding intermediate E. So, this should be E and this should be plus now. Now, I have to see whether you can write how many resonance structure, how many more resonance structure. From there, this is one of the nicest way of doing it though. People do calculation all these things, but they are somewhat I mean not when you do and how do you do and all these things are there, but here is very concrete, and so you can predict very well the reactivity. And other thing among the you have already said this neighboring participations already known. So, especially the ring opening reactions. Ring opening reactions, I missed a point though. Ring opening reaction can be assisted by, like what you said, what we have seen, by protonation. It can be also assisted by quaternization. So, if you have R alkyl group, nitrogen is quaternized, opens up. Then also Lewis acid like BF3 also catalyzes that. And then other thing is sulfone groups, electron withdrawing group, presence of electron withdrawing group. Let us say this is a case of aziridine, for example, aziridine nitrogen, if it is a sulfone group, that can open up. And lastly, I think since still we can see here, let us say if you have E here and E here. So, you have a group, let us say R, the aziridines often opens up to give you so this is elite, this is elite, that means this is dipole, right. So, 1,3 dipole is generated by aziridine, and this is very true for the aziridine cases, but there are epoxide also there are cases known. So, if you are interested, I can give you a homework. No, there is a homework though, and like say, no, I think I will skip it, fine.